For as long as we've looked up, we have been asking the same two questions. Where did all of this come from, and how will it all end? For the better part of a century, science offered an answer to the first, an origin tale both beautiful and terrifying in its simplicity. In the beginning, there was nothing, and then there was everything. The Big Bang, a singular violent act of creation that birthed space, time, and every star in the heavens. This is the foundation of modern cosmology. It gives our universe a clear beginning, an origin we can trace, quantify, even model. It's a comforting thought in its own way, a creation myth, but written in the precise language of mathematics. But what if this story is a lie? What if the Big Bang wasn't the beginning at all? What if it was just an aftershock, the result of an event far older, far larger, and far more terrifying than we have ever dared to imagine? There is a theory, born from the most advanced corners of physics, that seeks to replace the Big Bang. It's an idea that solves some of the deepest puzzles in cosmology, but in doing so, it opens the door to a vision of the universe so profoundly disturbing, it keeps the very scientists who study it awake at night. According to one unnerving theory, our universe was not born from a single point, but was blasted into existence by a violent encounter in a hidden dimension. A brutal encounter between unseen realities. To understand this chilling alternative, we first need to let go of our most basic assumptions about reality. Forget the idea of our universe being everything there is. Instead, imagine it as a single, three-dimensional sheet, a membrane. This is an idea that comes to us from the bleeding edge of theoretical physics. M-theory, an extension of string theory. In this framework, our universe is what's known as a brain. Think of our universe as a single page in an infinite book. All of our reality, every galaxy, every star, every atom in your body is stuck to the surface of this page, this cosmic brain. We can move up, down, left, right, forward, and back, but we can never leave its two-dimensional confines. But this page is not made of paper. M-theory suggests a much stranger reality. A brain is not composed of particles. It is the fundamental substrate upon which particles are permitted to exist. The matter and forces of our world are envisioned as open-ended strings, their ends permanently anchored to our reality. This means the very laws of physics might not be universal truths, but merely the local laws of our specific membrane, dictated by its unique properties. And in this model, our page is not alone. The space between the pages, the gap that holds all the different realities, is called the bulk. It is a silent ocean, defined by the absence of our physics, while other forces, like electromagnetic and nuclear force, remain trapped in our universe. Gravity roams freely between worlds, carrying whispers of other realities, and perhaps sharing the void with other, stranger things that drift in the dark. And floating in that bulk, parallel to our own reality, could be other brains, other universes, silent, invisible, and terrifyingly close. We can't see them, we can't touch them. The fundamental forces that govern our world are stuck to our brain, unable to cross the void. Just like two pages in a closed book don't touch, these universe sheets could be right next to us in a higher dimension, yet remain completely unreachable for a while. The ekpyrotic theory, first proposed in 2001 by physicists Justin Corey, Bert Ovrutt, Paul Steinhardt, and Neil Turok, posits a new origin story. It gets its name from the ancient Greek word ekpyrosis, a term used by Stoic philosophers. Ekpyrosis described a cosmic cycle in which the universe is periodically destroyed by a great fire, only to be reborn from the ashes. The name is no accident. According to this model, the Big Bang was not an explosion from a single point. It was a collision between two brains. Imagine two such universes, existing for eons in a cold, dark and empty state. For trillions of years, they float parallel to one another. Then, drawn together by a force that can pass through the bulk, gravity, they begin to move. Slowly at first, and then with gathering purpose, they fall toward each other. The climax of this cosmic drift is not an explosion in the traditional sense. It is a collision, a cataclysmic impact on a scale that dwarfs human comprehension. As one of its architects, Princeton's Paul Steinhardt, puts it bluntly, the ekpyrotic model doesn't begin with a bang, it begins with a crash. In that instant, the immense kinetic energy of the impact is converted into matter and radiation. The universe becomes incredibly hot and dense, sparking the expansion that we observe today as the aftermath of the Big Bang. Our entire cosmos, our past, our present, our future, is nothing more than the scar tissue from a dimensional car crash you will never see. This isn't just a different version of the Big Bang. It is a fundamental reframing of our place in existence. We are not the star of the show. We are the debris from an accident. Now, a theory this radical can't survive on shock value alone. It has to work. It has to explain the universe as we see it. And this is where the ekpyrotic model becomes truly compelling and perhaps even more unsettling. The first and most significant is the singularity. The Big Bang theory begins with a point of infinite density and zero volume. This isn't just an extreme concept, it's a point where physics itself ceases to exist. General relativity breaks down. The laws that govern the universe simply vanish. Scientists have always been deeply uncomfortable starting their most fundamental theory with a moment of mathematical nonsense. The ekpyrotic model elegantly sidesteps this problem. How? By declaring that there was no singularity. There was no moment when everything was compressed into a single point. Instead, there was a pre-existing state. Two cold, nearly empty three-dimensional brains. The universe had a past before the bang. Time didn't begin 13.8 billion years ago. It may have no beginning at all. The philosophical consequences of an eternal universe are staggering, but for this new theory to be taken seriously, it couldn't just tell a different story. It had to solve the very same deep paradoxes that its chief rival, cosmic inflation, was created to fix. And not just minor academic quibbles, gaping holes in the standard model, contradictions concerning the very shape and uniformity of our cosmos. These holes are better known as the horizon problem and the flatness problem. The horizon problem is this: the universe is astonishingly uniform. The temperature of the cosmic microwave background, the leftover heat from the Big Bang, is almost exactly the same in every direction we look. But according to the standard Big Bang, opposite ends of the observable universe should never have had time to talk to each other, to exchange heat and even out their temperatures. How did they become so perfectly coordinated? Inflation theory solves this by proposing a period of hyper-fast, exponential expansion right after the bang, stretching a tiny uniform patch of space to cosmic size. The ekpyrotic model achieves the same result through the complete opposite means: slow contraction. In the long period before the impact, the two brains are not just falling towards each other. The space on the brains themselves is gradually, gently contracting over an enormous timescale. This slow squeeze gives all the different regions of the brain universe ample time to interact, to smooth out any wrinkles, and to reach a uniform temperature. By the time the encounter happens, the universe is already smooth. No hyper-expansion needed. Then there is the flatness problem. Our universe appears to be geometrically flat, meaning that, on the larger scales, parallel lines don't curve, and the rules of geometry behave as if space were stretched out on a perfectly even sheet. This is a very specific and unstable state. Any slight deviation from perfect flatness in the early universe should have been magnified over billions of years, creating a cosmos that is either closed and spherical or open and saddle-shaped. Yet somehow, the universe has remained balanced on this razor's edge, so precisely that it suggests some powerful mechanism was at work in the earliest moments, smoothing space-time into near-perfect equilibrium. Inflation solves this by stretching space-time so much that it appears flat, just as the surface of the Earth appears flat to someone standing on it. The ekpyrotic model, on the other hand, uses its long period of slow contraction to iron out any curvature, flattening space long before the bang ever occurs. It solves the same problems, but its mechanism is darker. Inflation is an explosion of creation from a tiny seed. Ekpyrosis is a universe that must die before it can be born. a long, cold, patient collapse before the fire of the clash. However, this elegant solution comes at a cost. The ekpyrotic model relies on physics that is, to put it mildly, exotic. To make the bounce work, the theory must embrace concepts that many physicists consider forbidden. It requires violating the null energy condition, a foundational pillar of general relativity, which in essence ensures that gravity is always attractive. To generate the repulsive force needed to push two universes apart, the model must invoke a form of exotic matter with such extreme negative pressure that it literally makes space-time fly apart. But the required physics gets stranger still, demanding the existence of so-called ghost fields, energies that border on paradox. A normal field has positive energy. A ghost field has negative energy. This isn't just a mathematical quirk, it implies a universe that is fundamentally unstable, one that could spontaneously decay into an infinite storm of particles, ripping itself apart from the inside out. For many, this is the theory's fatal flaw, a vision of the cosmos built on a foundation on what many consider fantasy. So, of course, the theory has its critics. One of the fathers of the inflation model, Alan Guth, expressed his skepticism, stating, "They need to make very strong assumptions about the initial conditions. They're really starting out with a universe that's already infinite and uniform." Another titan of cosmology, Andre Lind of Stanford University, has been even more critical, arguing that the brain interactions required to produce the galaxies we see are highly specialized and unrealistic. He claims the brains would not be uniform enough to account for the smoothness of our cosmos. This scientific debate is crucial, but it's what comes next that truly elevates the ekpyrotic model from a mere curiosity to a source of existential dread. It makes unique, testable predictions. This isn't just a philosophical story, it's a hypothesis we might one day be able to prove or disprove. The key lies in gravitational waves. Both inflation and ekpyrosis would have produced a background of gravitational waves in the very early universe. But they would have produced a different kind of background. Inflation predicts that these waves should be stronger on larger scales, what physicists call a red-tilted spectrum. The ekpyrotic theory, however, predicts the opposite, a blue-tilted spectrum, with gravitational waves being stronger on smaller scales. These primordial gravitational waves would leave a faint, distinctive fingerprint on the cosmic microwave background, a mark we haven't yet detected. Our instruments simply aren't sensitive enough, but a new generation of telescopes may soon change that. Imagine a day, not too far from now, a team of scientists analyzes years of data, filtering out the noise from the cosmos, and they find a signal, a faint hum from the dawn of time. And that signal is blue-tilted. In that moment, our entire understanding of reality would shatter. The confirmation would be chilling. It would mean that the ekpyrotic model is not just a wild idea, but a plausible description of our origin. It would mean brains are real, the bulk is real, and the forces that govern our existence are not contained within our universe, but are products of a higher dimensional mechanic we are only just beginning to glimpse. Could we ever detect the bulk directly? Probably not. It is a space beyond our perception. But some physicists are searching for tiny anomalies in the strength of gravity, looking for signs that it might be leaking away into these extra dimensions. A ghostly clue that we are not alone in the cosmos. Experiments like the Large Hadron Collider and precision tests of Newton's inverse square law at sub-millimeter scales are probing for deviations that could hint at hidden spatial dimensions. The testability of the ekpyrotic model is unsettling, but the theory has an even more disturbing extension. Some versions of it are not a one-time event, they are cyclic. In this cyclic model, the collision that created our universe wasn't the first, and it will not be the last. The brains collide, bounce off each other, and slowly pull apart. As they separate, the universe on their surface blooms, fades, and withers into silence. It's slow heat death, just as standard cosmology predicts. But eventually, the brains stop, and the cycle begins anew. They are drawn back together, gradually at first, over unimaginable spans of time, until they collide again, wiping the slate clean and igniting a new Big Bang, a new universe, born from the ashes of the old. But how does a universe bounce? A collision of such finality shouldn't just rebound. It should end in a permanent fusion, a final death. The theory demands an answer, and it finds one not in a force we know, but in a law that awakens only at the end of all things. In the final moments before impact, as the gap between realities shrinks to less than an atom's width, the energy density becomes so extreme, it triggers a phase change in the fabric of space-time itself. The universe's crushing energy turns against its own collapse, generating a violent phantom repulsion. This is the engine of the bounce, a ferocious, calculated shove that not only prevents annihilation, but reverses it, turning the grave of one cosmos into the cradle of the next. This idea utterly demolishes our concept of linear time. There was no beginning, there will be no end, just an eternal loop of birth, death, and violent rebirth. As one Science News article described it, our universe may be just the latest phoenix in a cycle of annihilation and rebirth. Think of the philosophical weight of that. There was no first cause, no let there be light, just a cold, indifferent cosmic machine ticking over and over. A universe that expands and collapses like a breath. A cosmic heartbeat that has been pulsing for eternity. All of history, every human triumph from philosophy to poetry, every act of love and every act of war is just a temporary ripple, a fleeting pattern of energy on a membrane doomed to be incinerated and reset. The standard Big Bang model, for all its strangeness, is still a story about us. Inflation theory often leads to the idea of a multiverse, an infinite lottery of bubble universes, where our existence is a lucky roll of the dice. We are special because we won. The ekpyrotic model offers no such comfort. It does not require a multiverse of infinite possibilities. It offers something far colder. A single recurring universe, or perhaps a pair of them, locked in a brutal deterministic dance. We are not special. We are simply what happens this time around. There is a final existential horror to this theory. It lies in the contrast between how the universe might end. In standard cosmology, the end is distant and predictable. Whether it's the heat death, a big rip, or a big crunch, these are processes that unfold over billions, even trillions of years. The universe has time. The death is slow. The ekpyrotic model introduces a far more immediate and terrifying possibility. If our universe was born from a collision, it can be destroyed by one. Right now, as you watch this, another brain could be out there in the bulk, a parallel universe, silent and unseen, on a destructive course with our own. We would never know it was coming. The forces that govern it are not our own. The light from its stars, if it has any, is trapped on its surface. It would be moving through a dimension we cannot perceive, a ghost ship in the cosmic night. There would be no warning, no signal, no gradual fade to black. One moment, our reality exists. The next, it is obliterated in a flash of energy, wiped clean by an impact with forces we can't see, can't predict, and can never hope to stop. Our existence, erased in an instant, not as part of a grand cosmic plan, but as a simple, mechanical consequence of higher dimensional physics. This is the ultimate horror of the ekpyrotic theory, not the speculation, but how plausible it could be. It replaces the single, explosive birth of our universe with something far more sinister, a cosmos born of violence, and perhaps doomed to repeat it forever. It leaves us with one final terrifying question.